Hello, everyone. Thank you for having me, and thanks to the organizers for putting together this very nice workshop. I'm going to switch gears a little bit and talk about something maybe less familiar to some of you, namely atmospheric flows with water. And this is joint work with my colleague Sam Steckman from UW-Madison and our former PhD student, Yeyu Zhang, who just took a assistant professorship at the Shanghai University of Finance and Economics. So everything I'm going to talk about today has indirect implications for both transport and mixing. But on the other hand, it's probably going to be the next step that's going to give us some direct results. So the question that we're asking is, when do high frequency propagating waves, such as the cloud waves on the left, when do those waves have an influence on the slowly varying large-scale structures in the atmosphere, many of which are responsible for our weather, such as jets in the forms of jet streams, large-scale vortices like hurricanes, persistent layers, atmospheric rivers, and so on. And there is a long history of study of fast-slow interactions for the dry dynamics without water, also known as unbalanced balanced interactions. And you can split the literature basically into two groups. There are numerical simulations that are performed at finite values of the Rossby-and-Froude numbers. So the Rossby number is inversely proportional to rotation rate, and the Froude number inversely proportional to the buoyancy frequency. And so obviously in numerical simulations, you have finite values. And in those simulations, there are oftentimes coupling between the fast and slow. And many times the fast waves can self-organize to create large-scale structures, such as jets and layers and vortices. On the other hand, there are rigorous proofs in the limit as these parameters go to zero that show something quite remarkable. That is that the slow dynamics completely decouples from the fast waves. And there were two groups that worked on these proofs in the 90s. The group of Embiid and Maida and co-authors, and Babin, Mihalov, and Nikolenko and co-authors. And they're a little bit different techniques. And so we are going to be following up today on the limiting dynamics using a technique very similar to Embiid and Maida. And also just want to note that before we started on this project, to our knowledge, the case of atmospheric dynamics with water and phase changes was wide open. So we're just starting out on this project now. Okay, so for the rest of the talk, I'm going to start by introducing the moist Boussinesq model that we use that includes phase changes of water. And then I'm going to talk about the technique that's called fast wave averaging that Embiid and Maida used and how we extend it. And in order to carry out this procedure, we need to be able to decompose the flow into the slowly varying part and the fast wave part. So I'll tell you how we do that in the case of phase changes, and then present the results, which will be partly analysis, some numerical simulations, and then a simple ODE model that helps us understand the mechanisms. Okay, so here's the Boussinesq model, and it has fast cloud microphysics. So what does that mean? Well, when vapor condenses to form liquid water, that's a microphysical process. And similarly, when water evaporates to form vapor. And these processes take place on the timescales of seconds to minutes. And so we can safely say that they are asymptotically fast compared to the other timescales in the problem, such as advection and rotation and buoyancy and even rainfall. So that's what we do. We take asymptotically fast microphysics, and that leads to the closed system of equations on this view graph. And so let me talk through those equations. So the top equation is just conservation of momentum. And there are two new effects that we have because we've included water. So the buoyancy term here in big brackets on the right has a new contribution from water vapor, QV, and then another contribution from liquid water, QR, and it's called QR because it's allowed to rain out. And then, so this term here, this buoyancy, is the total gravitational force per unit volume, including the water contributions, and the black contribution is the contribution from dry air, written in terms of a temperature. Then we also need to include a new equation for the total water, which in our model is just the sum of vapor plus liquid. And the equation for total water is conservation following fluid parcels, apart from a rainfall term with a parameter VT, which represents the rainfall speed, if the liquid is allowed to fall out in the form of rain. So new equation. And then the other notable thing about this system is that we've written the energy equation in terms of what's called the equivalent potential temperature, theta E. Theta E is the sum of the potential temperature and an appropriately scaled water vapor. And the reason why it's nice to do that is because that equation appears in conservation form. So there is conservation of this equivalent potential temperature following fluid parcels, which is nice for the analysis. And so as usual, we've decomposed all of the thermodynamic variables into a background prescribed function of altitude z, and then the fluctuating part, and we're trying to predict the fluctuating part. And here, of course, I'm talking about stable stratification. So theta, for example, is increasing as you go up. Okay, so stable stratification, and this system is closed. And we could also write it in abstract formulation in terms of the state vector, this bold V, which includes the three components of velocity, the equivalent potential temperature, and the total water. And in terms of these operators, so L here is the operator that includes rotation and buoyancy. And we're going to be considering strong rotation and strongly stable stratification. So there is a large parameter 1 over epsilon multiplying this operator L that includes rotation and buoyancy, and our Rossby and Froude numbers are equal to epsilon, which we're taking to 0. Now we have two Froude numbers because we have a background temperature profile and a background water profile, both of which are assumed to be put us in stable situation. So the buoyancy and rotation operator has a large parameter in front, it's dominant, and then we have the quadratic nonlinearity. And we're going to be thinking about these equations in a periodic domain where the initial condition is just denoted V bar. Okay, so I want to set the stage for this work by showing you right up front some results of numerical simulations. We can just solve these equations numerically. And here in the different columns, I have, well, starting on the left, I'm showing you the total water. This is dk from random large-scale initial conditions where the value of epsilon is 0.1, so relatively small. The liquid is not allowed to fall out, so the parameter VT that I showed you is 0, so the liquid water does not fall. And there is a saturation deficit of 0.5, which means that when the total water is greater than that value 0.5, then we have liquid, and those are the red blobs in these pictures. And when the total water is smaller than 0.5, we have water in the form of vapor, and that's the blue. So we're solving these equations numerically. This first column is total water evolving for some short times, t up to t equals 0.2. And then what we've done is decomposed the water into its slowly varying part. That's the middle column, the balanced water, and then its fast wave part, which is the right column. And I should mention here, before I talk about these, I should have mentioned that in these equations, written in terms of the primary variables, velocity, temperature, and water, all these variables are mixed in the sense that they have a slowly varying part and they have a fast wave part. And so here, back to our simulations, we can decompose into those two pieces. And what you should notice here from the middle column, which represents the slowly varying part, that indeed you do not see much change in the red blobs and the blue blobs as you move down in time on these short time scales. Whereas in the right column, the fast wave part, much more significant variation in the fast wave part. Okay, so we can monitor these quantities, split them into their slow and fast parts, and then we can look at longer times, order 1 times, and it's the same 3 columns here. Total water on the left, slowly varying part in the middle, and fast wave part on the right, up to, but now time scales of order 1. And you see that the slowly varying part does vary, and it varies significantly on order 1 time scales. And what we're asking here is how much of that variation that we see on the order 1 time scales is due to interactions with the fast wave part, or would that evolution take place on its own without interactions with the waves? So that's what we're trying to answer here. Okay, so what's the idea? What's the technique we're going to use? It's called fast wave averaging. And again, we're taking the limiting dynamics here for both Rossby and Froude going to 0. And the idea is just to take advantage of this small parameter and write down a 2 time scale perturbation expansion where there is a new time scale tau, which is t over epsilon. So when t is order epsilon, then tau is order 1. And when t is order 1, then tau is going to infinity. So straightforward perturbation expansion in powers of epsilon, and then plug this expansion into the equations, collect terms order by order, and see what we can learn. And so we go ahead and do that, and the biggest terms are at order 1 over epsilon, and give us an evolution equation for V0. It's a very simple equation. It's homogeneous, and it can be solved in terms of an integrating factor and the initial condition V bar. And then we can go to the next order, which is order 1, to write down an evolution equation for V1. And that is also a simple equation, but it's non-homogeneous. And now the non-homogeneous term involves V0, which we had found at the previous order. And so again, we can use an integrating factor to solve this, but we remember that we want to preserve the ordering of the expansion. And so there is a constraint on this equation to disallow secular growth in time. And so when we apply the condition for sublinear growth of V1, that gives what's known as the fast wave averaging equation. That's this equation in blue in terms of these integrals and the operators L and B and the inverse of the integrating factor, another operator A. So once we have this condition, then we can take this system, project this equation onto the slow modes, and then assess coupling on the right-hand side and ask what are the terms on the right-hand side in terms of the slow modes and the fast modes. Okay, so that's the technique. And in the case of dry dynamics, the operator L is linear, and in fact, it's constant. So one can carry out this method fairly straightforwardly using Fourier analysis. First, you have to find the slow modes, there is only one in the case of the dry dynamics. It's called the potential vorticity, and it's the sum of the vertical vorticity and the vertical derivative of temperature, a very important quantity in atmospheric dynamics. And the fast wave averaging equation, which is here in red, is just the statement that potential vorticity is conserved following fluid parcels. And the advection velocity that appears is the slowly varying part of the velocity, here denoted U sub PV. So one can see that in this equation, there is only a slow nonlinear interaction. And so the equation for the slow PV is completely decoupled from the fast waves. And that is the result that Embiid and Maida derived rigorously, and that we're going to try to extend. And so we can go back now to the moist equations with phase changes. And the key observation here is that now this term that involves rotation and buoyancy changes its functional form because the buoyancy changes its form as we cross a phase boundary from an unsaturated region where the liquid is only vapor to a saturated region where the water is liquid. So the buoyancy changes its functional form, and that's the hard part about this problem. And we've chosen to make that explicit by using these Heaviside functions. So HU is for the unsaturated domain. So it takes the value 1 if total water is less than saturation, and then water is vapor, and it's 0 if water is greater than the saturation value. And then HS is just 1 minus HU. And so this is just a different way of writing the buoyancy that makes the phase boundaries explicit. And these phase boundaries, as the flow evolves, are determined by the full evolution, so the full state vector, which means we actually have now a nonlinear operator for our buoyancy operator that depends on the fast time scale tau. So it's a harder problem in from several points of view. And so what we have to do to adapt this fast wave averaging to the case with phase changes is first think pretty carefully about the treatment of these Heaviside functions. We have to go back and find the slow and fast variables that are appropriate for the new system, derive this fast wave averaging equation, project onto the slow modes, and now remember, we cannot use Fourier analysis because of the piecewise nature of the buoyancy operator. And so we have to rely purely on structural properties of the operators in physical space. So that's what we do, and it's a purely formal analysis at this stage, but I can show you what we get. And the interesting thing, of course, that we get is we can no longer, I have to show you, yes, I have to show you what the slow variables are. So in the moist system, we can find them. The slow quantities are just quantities that do not change in time as the small parameter goes to 0. And they're just, it's just basically finding the null space of that operator L. And now there are two quantities. There is a potential vorticity variable, which looks the same as the dry case, except that temperature is replaced by equivalent potential temperature. And there's a new quantity that's slowly varying, which is the sum of total water and equivalent potential temperature. And we just named it M for moisture. So two slowly varying quantities now. And so now we can take the fast wave averaging equation, project onto these slow modes, and assess the coupling on the right-hand side of that equation. And as I was mentioning, it's now a formal analysis. And the interesting thing that we get is different terms that do couple the fast and slow modes in both of the equations for M and PV. And these are terms that we cannot a priori show go to 0. There are other terms here that we can show are 0 using the structural information of the operators, but many that remain. And for example, in the equation for M, we have a new advection velocity, which is a time average over the wave component of the velocity, which would not be there in the dry dynamics, obviously, and other fast-slow coupling terms in the equation for PV. So these averages that appear here in these equations are averages over the timescale as tau goes to infinity. All right, so many terms that appear to imply coupling between the fast waves and the slow components. And so then what we did is we went to the numerical simulations to try to see if we could assess these terms, at least for trends as epsilon goes to 0. Obviously, we cannot take the limit as epsilon goes to 0, but we can decrease epsilon systematically from, for example, 1 to what we went to is 10 to the minus 3. And we can evaluate the terms that appear on the right-hand sides of that fast wave averaging equation. And so that's what I'm showing you here. And I'm showing you two different types of terms. On the left is amplitude of slow coupling terms in the equation for PV as a function of epsilon varying from 1 to 10 to the minus 3. And then on the right are some fast coupling terms, again, in the equation for PV. And we've got dry simulations here in red, phase change simulations in blue, and there are two different symbols for two different resolutions, just to give you some confidence that these are becoming well resolved. And so what we see on the left here is that for both the dry in red and the phase change simulations in blue, this slow coupling term remains order 1 as we decrease epsilon, which it should, because the slow coupling terms are always going to be the important or unimportant source of variation in the evolution of the slow terms, PV and M. On the right, fast coupling, there is a pretty dramatic difference between the behavior of the fast coupling in the dry versus phase change. So again, the dry simulations is red, and what we see here is as we decrease epsilon from 1 to 10 to the minus 3, there is roughly a linear decay in the amplitude of these fast coupling terms. And we know from the rigorous proofs that these terms must go to 0 in the limit. So that's reassuring that they behave as they should. And what we see for fast coupling in the phase change case is that those terms remain hovering around order 1 as we decrease epsilon from 1 to 10 to the minus 3. So that's pretty strong support that those terms do not go to 0, as we could not show analytically that they would go to 0. So that's support from the numerical simulations. And then we'd like to say, well, why do these terms remain 0 and not go to 0 as they do in the dry case? And to get some initial insight as to the mechanisms for non-zero coupling, we wrote down a simple ODE model where we keep only vertical velocity and then the two different buoyancies, an unsaturated buoyancy BU and a saturated buoyancy BS, functions of time. And so here, M is simply a parameter, and the condition for saturation to change from unsaturated to saturated is when BU is equal to BS. So what we can do here is we can solve exactly this ODE system, starting from, for example, unsaturated initial conditions. And in that case, we would start by using the equations for W and BU, evolve exactly in time until we hit the saturation condition, which is BU equals BS, and then switch over to solving the system for vertical velocity and saturated buoyancy BS, and so on. And in the individual regions, we'd simply have a harmonic oscillator equation for either BU or BS when we eliminate vertical velocity. So it's very simple to do. And here's a sketch of the solution for the special case of m equals 0, but it's the same idea for non-zero m. And so this is a sketch of what would be the total water in the numerical simulations or the unsaturated buoyancy in the ODE model. The phase boundary is now the pink line, which is the x-axis. And so we start by solving in the unsaturated domain, and we have a wave, and that wave has a certain buoyancy frequency and wavelength associated with it. We evolve the wave in time until we get to the saturation condition, and then we have to switch over to solving the equations in the saturated domain. And in that domain, there is a different buoyancy frequency and a different wavelength. And so we have this piecewise wave that we can continue solving as long as we want. But the thing to notice here is that when we cross a phase boundary, we have a different wavelength. And so when you take a time average, you would not expect to have zero time average. And that is at least one of the mechanisms that's going on in the numerical simulations. And we can check that actually by looking at waves in total water and any other quantity. And so we actually have pretty strong confidence now that this coupling phenomena is real and will persist as epsilon goes to 0 in the limiting dynamics. And so I'll just finish up here and summarize. So we've done a formal calculation that strongly suggests that coupling between fast and slow components will exist for the limiting dynamics when phase changes are present. We have some numerical simulations for decreasing epsilon that also strongly suggest that coupling will persist. And now what's remains to finish up is to make the analysis more rigorous and also go back to that other literature, which is the simulations for finite values, and start understanding the statistically steady states for finite parameter values, which I think will give us direct information about transport and also mixing for the finite parameter values. And I think that'll be a really interesting study to follow up. So thanks for your attention.